Hello everyone and welcome to today's presentation. I'm excited to guide you through an overview of slab types and MEP coordination. On this first slide, you'll see the title, Overview of Slab Types and MEP Coordination, along with the subtitle. We'll be exploring different slab types, flat, solid, Horid, and reverse beam slabs, shown side by side for comparison. You'll notice their column spans vary from 4 to 8 meters, and their self-weight ranges between 4.5 and 5 kilonewtons per square meter. Throughout the presentation, we'll also look at icons representing structure, rebar, electrical, plumbing, and HVAC considerations. Let's dive in and see how these elements come together in our projects. Let's take a closer look at the flat slab system. The slab itself is 230 millimeters thick, which provides a good balance between strength and material efficiency. Additionally, we have drop panels measuring 500 by 500 millimeters, which are crucial for enhancing the load distribution, especially around columns. Moving on to reinforcement details, the top reinforcement consists of O-12 bars spaced at 150 millimeters, while the bottom reinforcement uses O-10 bars, also spaced at 150 millimeters. These reinforcement bars are essential for handling tension and compression forces within the slab. The span, or the distance between supports, is 8 meters, making this a relatively large span that requires careful design considerations. The slab's weight is approximately 5 kilonewtons per square meter, which impacts the overall structural load. It's important to maintain at least 50 millimeters of clearance from the rebar clusters. This spacing ensures proper concrete placement and curing, as well as ease of reinforcement installation. Throughout this process, we use various icons, like formwork, rebar, conduits, sleeves, and curing, to represent different components involved in constructing this flat slab system. Keeping these details in mind helps us ensure a safe, durable, and efficient structure that aligns with our overall project goals. Let's take a closer look at the solid slab supported by normal beams here. The slab itself is 150 millimeters thick, resting on beams that measure 300 by 500 millimeters. The reinforcement details include top bars of O-12 spaced every 200 millimeters and bottom bars of O-10 spaced every 150 millimeters. This reinforcement configuration is crucial for the slab's strength and durability. The span of these beams ranges from 4 to 5 meters, which influences the overall design and load distribution. Speaking of loads, the slab is designed to handle approximately 4 kilonewtons per square meter. Now, moving to the services, electrical conduits, specifically O-25 millimeters, are placed in the top zone of the slab for easy access and integration. Plumbing pipes, with a diameter of O-75 millimeters, are positioned mid-span to optimize space and functionality. Lastly, HVAC ducts are routed below the beams, ensuring efficient air distribution without interfering with other structural components. All these elements, beams, reinforcement, and services, are interconnected and vital for creating a safe, functional, and well-integrated building. Let's take a closer look at the Horid, or hollow block slab, design. The ribs are spaced at 500 millimeters on center, which provides a good balance between strength and material use. The topping thickness is 60 millimeters, offering a solid surface for finishes and load distribution. In terms of reinforcement, we have bottom reinforcement with a diameter of 12 millimeters spaced at 200 millimeters, and top reinforcement with 8 millimeters, also at 200 millimeters. This reinforcement pattern helps manage tension and compression effectively within the slab. The span for this slab is 6 meters, making it suitable for medium to large open spaces. The total weight of the slab is approximately 3 kilonewtons per square meter, which is important for structural calculations and load considerations. An important point to note is that conduits are only placed within the topping layer, and we should avoid placing them in the ribs. This helps maintain the structural integrity of the ribs and ensures proper load transfer. Finally, you'll see icons representing different elements: bricks for blocks, toolbox for ribs, light bulb for conduits, droplet for sleeves, and building construction for pouring activity. These visual cues help us quickly identify key components and steps in the construction process. This approach ensures we're designing safe, efficient, and functional slabs that align with our overall project goals. Let's take a closer look at the reverse beam system and how we route the MEP services. The beams are typically 300 by 500 millimeters and are positioned about 150 millimeters above the slab. This height allows us to efficiently integrate the various services without compromising structural integrity. The top reinforcement consists of O-stroke 16 bars spaced at 150 millimeters around the beam, while the slab itself is reinforced with O-stroke 10 bars also at 150 millimeters. This reinforcement setup ensures the system can handle the loads and span lengths effectively. Speaking of spans, these beams typically cover distances between 4 to 6 meters, supporting a load of around 4.8 kilonewtons per square meter. This gives us a good balance between structural strength and flexibility in design. Now, the soffit, or the underside of the beam, is kept flat to facilitate the installation of various HVAC components, fire safety systems, drainage, and cable trays. We use color coding: blue for HVAC ducts, red for fire systems, gray for drainage, and yellow for cable trays, to keep everything organized and accessible. Finally, the icons on the slide: building for the reverse beam, wind for ductwork, droplet for drains, high voltage for cable trays, and for fire safety, help us quickly identify each component's role in the system. Overall, this integrated approach ensures our structure is both functional and efficient for all MEP services. Let's take a closer look at the Saudi Code and best practice summary. When it comes to the SBC guidelines, specifically 301, 304, 501, and 801, there are some key points to keep in mind. For conduits, they should be installed with a clearance of 25 to 75 millimeters from rebar to ensure safety and compliance. Also, HVAC systems need to be placed in beam-free zones to avoid structural conflicts and facilitate installation. Another important aspect is the grouping of plumbing corridors. Keeping these corridors organized not only improves efficiency, but also makes future maintenance easier. Penetrations through walls or slabs should be limited to 20% of the rib width, which helps maintain structural integrity and prevents unnecessary weakening. You'll notice the icons on the slide. Blue Book represents codes, which guide our compliance. Brick stands for quality, emphasizing the importance of standards. Toolbox points to safety measures, droplet highlights curing practices, and gear relates to coordination among different disciplines. Overall, these guidelines are designed to promote a coordinated, safe, and high-quality construction process, aligning with our overarching goal of delivering a resilient and compliant building project. Let's take a closer look at this combined 2D technical drawing. Here, we see different types of slabs positioned side by side: flat, solid, and Horid. Each of these elements has specific characteristics and functions within the structure. The flat slab spans about 8 meters and is designed to handle a load of 5 kN per square meter. Flat slabs are often used for their ease of construction and flexibility for future modifications. Moving on, the solid slab extends 5 meters and supports a slightly lower load capacity of 4 kN per square meter. Solid slabs are typically more robust, used where greater strength is needed. Lastly, we have the Horid slab, which spans 6 meters and is rated for 3 kN per square meter. You'll notice the icons here. The brick icon bricks indicates flat slabs, the toolbox for solid, and the abacus for Horid. These help us quickly identify the types of slabs in the drawing. Additionally, the drawing shows reinforcement bars, marked with gear, which are crucial for structural integrity, especially in areas subjected to tension. The droplet icon indicates drainage routes, essential for effective plumbing and water management within the slabs. All of these elements are integrated, showcasing the coordination between structural components and MEP routing. This comprehensive view helps us understand how the different slabs work together to support the overall building design, ensuring safety, functionality, and efficiency. Let's take a closer look at the summary table comparing SBC 304 and SBC 501. First, for the flat section, we have a thickness of 230 millimeters with a span of 8 meters. The reinforcement details are O/12 at 150 millimeters and O/10 at 150 millimeters. The allowable load is 5 kilonewtons per square meter and the L250 deflection limit. Moving on to the solid section, it's slightly thinner at 150 millimeters with a shorter span of 5 meters. The reinforcement here is O/12 at 200 millimeters and O/10 at 150 millimeters, supporting a slightly lower load capacity of 4 kilonewtons per square meter, but still maintaining the same deflection limit of L250. Next, the horizontal or Horid section is interesting because it has a combined thickness of 250 plus 60 millimeters, totaling 310 millimeters, and a span of 6 meters. The reinforcement is O/8 at 200 millimeters and O/12 at 200 millimeters. The load capacity drops to 3 kilonewtons per square meter, with a slightly more conservative deflection limit of L300, which makes sense given the increased thickness. Finally, the reverse section combines 150 plus 500 millimeters, totaling 650 millimeters in thickness, with a 6-meter span. The reinforcement is O/16 at 150 millimeters and O/10 at 150 millimeters, supporting a load of 4.8 kilonewtons per square meter, again with an L250 deflection limit. Overall, what this table shows is how different structural configurations, like thickness, reinforcement, and span, affect the load capacity and deflection limits. It's a great way to compare the different SBC types and understand their specific applications based on structural demands.